There is a possibility, taken seriously by some philosophers and physicists, that everything you have ever touched, seen, or felt has been the output of a process running somewhere else. Welcome to the Sleepy Lab. Tonight, we drift through one of the quietest and most unsettling ideas in modern thought, the possibility that the universe itself is a kind of computation, and that you, lying here in the dark, might be part of it. If that stirs something in you, consider subscribing, one sleepy soul at a time. Now, let's begin. In 2003, a philosopher named Nick Bostrom published a paper, not a thought experiment passed between colleagues over coffee, a formal academic argument with premises and logic and a conclusion that followed step by careful step from assumptions that are difficult to dismiss. The paper was called, "Are You Living in a Computer Simulation?" And the question was not rhetorical. Bostrom's argument takes the shape of what philosophers call a trilemma, a structure in which exactly one of three statements must be true, though we cannot yet know which one. The first possibility is that civilizations like ours almost always go extinct or collapse before they ever develop the technology to run detailed simulations of minds. The second is that civilizations capable of running such simulations simply choose not to, perhaps out of ethics, perhaps out of indifference, perhaps for reasons we cannot yet imagine. The third possibility, the one that tends to linger, is that we are almost certainly living inside a simulation right now. One of those three things is true. Bostrom does not claim to know which. He assigns, roughly, equal weight to each branch, a kind of philosophical humility held very still. But to understand why the third branch is even on the table, it helps to follow the logic slowly. The argument begins with a single assumption, not a certainty, an assumption that consciousness, the felt sense of being someone, of experiencing something, does not require biology to exist. That it could, in principle, run on other substrates. On silicon, perhaps. On something we have not yet built or named. The idea is sometimes called substrate independence, and it is not a fringe position. It sits at the center of serious debates in philosophy of mind and cognitive science. If that assumption holds, if minds can be made from something other than neurons, then a sufficiently advanced civilization could, in principle, create minds that are not born but instantiated. Minds that wake into a world that feels entirely real, because for them, it is. Now consider the numbers quietly. A civilization that survives long enough and grows powerful enough, million, perhaps more. Each simulation containing minds that believe themselves to be original, biological, embedded in a real and unmediated world. The ratio of simulated minds to original minds under those conditions would be vast, not slightly larger, astronomically larger. 100 simulated minds for every real one would be a conservative estimate. The actual ratio, if such civilizations exist and run such simulations, could be far beyond anything we have words for. And here is where the logic turns quiet and strange. If you were to reach into that entire population of minds, all the original ones and all the simulated ones together, and draw one at random, the odds that you would draw a simulated mind would be overwhelming. Not because simulation is proven, but because of simple proportion. There would just be so many more of them. Bostrom's argument does not say the simulation is real. It says that if minds can be simulated, and if civilizations tend to survive long enough to simulate them, then the prior probability of being an original mind is very small. It is a statistical argument dressed in philosophical clothes, and it is harder to dismiss than it first appears. The first branch of the trilemma offers one escape. Perhaps civilizations like ours almost never make it. Perhaps there is something, a filter, a tendency, a fragility built into the nature of intelligent life that ends things before the technology ever matures. If that is true, then the population of simulated minds never grows large, and the statistical pressure dissolves. The second branch offers another escape. Perhaps the technology is eventually built, but the civilizations that build it choose restraint. Perhaps running a simulation of conscious beings is considered, by those advanced enough to do it, to be something that should not be done. An ethical line drawn quietly across the history of every civilization that reaches that threshold. If either of those branches is true, we are probably not simulated. We are probably original, biological, embedded in a universe that exists without a programmer. But if neither of those branches is true, if civilizations do survive and do run simulations and do so in large numbers, then the third branch follows almost automatically, and we would have no way of knowing. Bostrom himself does not advocate for the third branch. He holds the trilemma open, like a door left ajar in a quiet house. He finds each branch genuinely plausible. He has said, in various interviews and writings, that he would not be surprised to learn that the first branch is true, that something tends to end civilizations before they reach that point. But he cannot rule out the third. What makes the argument unusual among philosophical ideas is how seriously it has been taken by people outside philosophy. Physicists have engaged with it. Mathematicians have tried to find its edges. Some have looked for ways to test it, or at least to find the places where it might leave a trace. We will follow those threads later in this series. The physicists searching for signs of a computational substrate in the fabric of space itself. The mathematicians asking whether the universe's structure is more consistent with a simulation than with raw, unmediated reality. But for now, it is enough to rest with the shape of the argument. One of three things is true. Civilizations collapse before they simulate, or they choose not to, or we are, in all likelihood, already inside. Bostrom published this in 2003. It was not the first time someone had wondered whether reality might be something other than it appears. Philosophers have circled this territory for centuries, in different languages, in different forms. But Bostrom's version was different. It was not a meditation on doubt. It was not a metaphor. It was a structured argument, with premises that could be examined and a conclusion that followed from them with a kind of quiet, uncomfortable logic. And it has not been refuted. Not because it is certainly true, but because the three branches of the trilemma are genuinely difficult to close. Each one requires something, a catastrophe, a consensus, or an acceptance that we cannot yet confirm or deny. So the door stays open. And somewhere in the space between those three possibilities, the question rests, not urgent, not alarming, just present, like a sound you cannot quite place in a room that is otherwise still. You are conscious. You are here. You are experiencing something right now, in this moment. Whether that experience is original or instantiated, whether it arises from neurons shaped by billions of years of evolution, or from something else entirely, it is, at least, real to you. And perhaps that is where the question begins. Perhaps that is where the physics begins, too. Because if the question is whether reality could be computed, the first place to look is not outward, toward the stars, but inward, toward the smallest possible scale of things, toward the floor of the physical world. And it turns out, there is a length so small that our best current theories of physics simply stop working below it. Not because we lack the instruments to measure it, though we do, but because the mathematics itself begins to break down. Space and time, as we understand them, lose their coherence at that scale. The equations return answers that are not just unknown, but undefined. That length is called the Planck length. It is approximately 1.616 times 10 to the negative 35 meters, a number so small it resists any ordinary comparison. If an atom were scaled up to the size of the observable universe, the Planck length would still be smaller than that atom. It is not merely tiny, it is the boundary of the describable. Below it, the concept of distance may lose its meaning entirely. Not just practically, not just for now, until better instruments arrive, but perhaps fundamentally. Perhaps there is no such thing as a length shorter than the Planck length. In the same way, there is no temperature colder than absolute zero. Not a gap in our knowledge, but a feature of reality itself. And some physicists take this seriously. They describe space at the Planck scale not as a smooth, continuous fabric, the way we tend to picture it, the way it appears in the equations of general relativity, but as something more like a lattice, a grid, a structure made of discrete units, each one the size of the Planck length, each one either occupied or not, each one a kind of minimum pixel of existence. This idea has a name. It is called discrete spacetime, or sometimes digital spacetime. And it is not a fringe position. It appears in serious research programs in quantum gravity, in loop quantum gravity in particular, where space itself is thought to be woven from finite, indivisible loops. Not infinitely divisible, not smooth all the way down, but granular, like sand that looks like a beach from a distance, but up close resolves into individual grains. The word digital is deliberate. It carries the same meaning it carries in computing, not digital as in modern, or digital as in electronic, but digital in the original sense, discrete, countable, made of distinct units rather than continuous flow. The opposite of analog, the opposite of smooth. And if space is digital in that sense, if it is made of irreducible units, if there is a smallest possible distance below, which nothing can be measured or even meaningfully defined, then the universe begins to resemble, at least structurally, something that could be computed. Not necessarily something that is being computed, that step comes later, and it is a large one, but something that could be, in principle, represented as a finite set of states, updated according to rules, one Planck length step at a time. This is where a physicist named John Wheeler enters the picture. Wheeler was one of the great theoretical physicists of the 20th century. He worked on nuclear fission, coined the term black hole, and spent decades thinking about the deepest structure of physical law. And late in his career, he arrived at an idea that he found both troubling and compelling. He called it from bit. The phrase is compact, almost cryptic, but what it points to is a profound reorientation of how we think about matter and information. Wheeler proposed that information is not something we extract from the physical world, a description we layer on top of reality after the fact. He proposed that information is prior to reality, that it underlies it, that every particle, every field, every physical thing that exists derives its existence from something more fundamental, from answers to yes or no questions, from bits. In Wheeler's vision, the universe is not made of matter that happens to carry information. It is made of information that happens to appear as matter. Every electron, every photon, every quantum of energy, each one, at its root, is the outcome of a binary distinction. A question asked of nature and answered, He was not speaking loosely. He meant it as a serious proposal about the architecture of reality, that beneath the fields and forces and particles, beneath even the space-time that contains them, there is something more primitive, the act of distinction itself, the difference between yes and no, between 1 and 0, between something and nothing. It from bit. The physical world, the it, arising from information, the bit. This is a strange idea to sit with. We are accustomed to thinking of information as something that exists about things, a description, a measurement, a record. Information lives in books, in signals, in the patterns of neurons firing. It is always information about something else, something more real, something physical. But Wheeler inverted that relationship. And he was not alone in finding the inversion worth taking seriously. The idea that information is not just a feature of the universe, but its foundation, that the physical is, in some deep sense, downstream of the informational, has attracted serious attention from physicists and philosophers in the decades since. It connects to the Planck scale in a quiet but important way. If space is discrete, if there is a smallest unit of distance, a minimum pixel, then the universe contains a finite amount of information per unit volume. Not infinite detail, not infinite precision, but a bounded, countable number of states. A universe with a resolution limit. And a universe with a resolution limit is a universe that could, in principle, be stored. Not easily, not with any technology we can imagine, but in principle, the information content of a finite region of space would be finite, bounded, representable. This is not yet the simulation hypothesis. It is something quieter than that. It is the observation that the physical world, examined closely enough, begins to look less like an infinite analog continuum and more like something that has structure at the bottom. Edges, units, a grain. Whether that grain is the signature of a computation running somewhere or simply the nature of space itself, that question remains open. Wheeler did not claim the universe was a simulation. He claimed something more modest and in some ways more unsettling. That information is real, that it is not a human invention layered onto a pre-existing physical world, but a fundamental feature of that world. Perhaps the fundamental feature. And if that is true, if reality is, at its deepest level, informational, then the distance between a physical universe and a computed one begins to narrow. Not to zero. The gap remains. The questions multiply rather than resolve. But the conceptual space between the universe obeys mathematical laws and the universe is a mathematical process becomes, at least, a space worth exploring. Quietly, without urgency. The way you might notice, lying still in the dark, that the boundary between your thoughts and the silence around them is not as sharp as it seemed. That the edges of things, examined closely, tend to soften. And below a certain scale, below the Planck length, below the last meaningful unit of distance, even the concept of an edge may dissolve into something that has no name yet. Something that physics is still learning to ask questions about. Claude Shannon was a mathematician working at Bell Laboratories in 1948. He was not, at the time, thinking about the nature of reality. He was thinking about telephone lines, about how much information could be sent through a wire without being lost to noise. And yet, the framework he built that year, quietly, most people outside engineering never read, turned out to describe something far larger than telephone lines. Shannon defined information mathematically, not as meaning, not as content, not as anything a human mind would recognize as significant, but as a measure of uncertainty reduced by a message. If you already know what someone is going to say, their words carry no information. If you have no idea, every word carries a great deal. Information, in Shannon's framework, is the gap between what you knew before and what you know after. That definition sounds almost too simple, but it has a consequence that took decades to fully absorb. It means information is not merely a human concept, not a label we attach to things that matter to us. Shannon's framework treats information as a physical quantity, something that can be measured, bounded, conserved, and lost. Something that behaves, in certain respects, like energy or mass. Something the universe itself appears to track. And once you accept that, once you allow that information is not just a description of reality but a feature of it, certain things that seem like metaphors begin to look like something more. One of those things is a black hole. A black hole is a region of space where gravity has become so intense that nothing, not matter, not light, can escape. For most of the 20th century, physicists assumed that anything falling into a black hole was simply gone, lost. That the information describing that object, its composition, its history, the precise arrangement of every particle it contained, was erased from the universe. Jacob Bekenstein was a graduate student in the early 1970s when he began to suspect that was wrong. He was studying the thermodynamics of black holes, the way they behave in terms of heat and entropy, and he noticed something that did not fit the standard picture. The entropy of a black hole, he proposed, was not proportional to its volume. It was proportional to its surface area, to the area of the boundary surrounding it, rather than the space within. This was a strange idea. Entropy is usually thought of as a property of the interior of a system, the number of ways its internal components can be arranged. The idea that a black hole's entropy lived on its surface, rather than inside it, seemed almost backwards. Stephen Hawking was skeptical at first, but when he applied the tools of quantum field theory to the problem, when he worked through the mathematics carefully, he found that Bekenstein was right, more than right. Hawking's calculations gave the relationship a precise mathematical form, now called the Bekenstein-Hawking entropy formula. It confirmed that the information content of a black hole is encoded on its event horizon, the spherical surface at the point of no return, and that this encoding has a definite, calculable limit. There is only so much information a given region of space can contain, and that limit is set not by the volume of the region, but by the area of its boundary. Sit with that for a moment. The amount of information inside a sphere is bounded by the surface of that sphere, not by what is inside, by what surrounds it. This is the holographic principle. The idea that the information content of any volume of space is fully encoded on the two-dimensional surface that encloses it, that a three-dimensional region of reality could, in principle, be completely described by data living on its boundary, the way a hologram encodes a three-dimensional image on a flat piece of film. The word holographic can sound like a metaphor, like a poetic way of gesturing at something vague, but it is not being used that way here. The holographic principle is a precise claim about the information-carrying capacity of space itself. It emerged from rigorous calculations about black holes, confirmed by multiple independent lines of reasoning, and it has since become one of the most productive ideas in theoretical physics. What it implies is quietly extraordinary. If the information content of a volume is encoded on its boundary, then the interior, the three-dimensional space you might think of as the real space, is, in some sense, redundant, not unreal, but derivable. The full description of what is happening inside can be read off from what is happening on the surface. This does not mean the world is flat. It does not mean the third dimension is an illusion in any simple sense. It means something more subtle and in some ways, more difficult to hold in the mind. It means that the dimensionality of space may not be as fundamental as it appears, that what we experience as depth, as volume, as the three-dimensional texture of the world may be a kind of projection, a higher dimensional structure arising from lower dimensional information. The way a shadow on a wall carries information about the object casting it, except in reverse. The shadow, in this analogy, is the three-dimensional world, and the object casting it is something flatter, something encoded on a surface we cannot directly see. Juan Maldacena would later give this idea a precise mathematical realization, a correspondence between theories in different numbers of dimensions that has been tested and confirmed in many contexts. But that comes later in the story. For now, it is enough to stay with the principle itself. The holographic principle did not arise from speculation about simulations. It arose from black hole thermodynamics, from the careful application of quantum mechanics and general relativity to the most extreme objects in the known universe. It is not a fringe idea. It is taken seriously by a large portion of the theoretical physics community, precisely because it emerged from such solid ground. And yet it leads somewhere that feels, at first, almost impossible to accept. If reality is holographic, if the three-dimensional world we inhabit is encoded on a two-dimensional surface, then the universe is, in a very specific sense, informational at its foundation, not made of matter that happens to carry information, but made of information that gives rise to the appearance of matter, space, and dimension. Wheeler's phrase returns here, quietly, it from bit, the physical from the informational, not as a slogan, but as a structural feature of the mathematics. Shannon defined information as the reduction of uncertainty. Bekenstein found that black holes encode information on their surfaces. Hawking confirmed it with numbers. And the holographic principle extended that finding to space itself, to every region, every volume, every corner of the universe you might choose to examine. Each of these steps was taken carefully by people working within the established methods of physics and mathematics. None of them set out to argue that the universe is a simulation. They were following the evidence where it led. And where it led was here, to a universe in which information is not a description of physical reality, but a constituent of it, in which the geometry of space, the very shape of the world, may be a consequence of how information is organized, bounded, and encoded. The distance between that picture and the idea of a computed universe is not nothing. There are still large gaps, still deep questions, still many places where the analogy breaks down. But the picture itself, a reality that is fundamentally informational, whose three-dimensional depth arises from two-dimensional data, whose structure obeys precise limits on how much can be known about any given region, that picture is not science fiction. It is, as best as anyone can currently tell, a feature of the universe we actually live in, resting now in the quiet, in the dark, in a space that may be deeper than it appears. And within that informational picture, there is one result that stands apart from the rest. One piece of mathematics so precise, so complete, that physicists still speak of it with a kind of quiet disbelief. It came from a physicist named Juan Maldacena. In 1997, Maldacena was working in a highly abstract corner of theoretical physics, studying a particular kind of curved spacetime called anti-de Sitter space. It is not the shape of our universe. It curves differently, closes in on itself in ways our cosmos does not. But it is mathematically tractable, and that made it useful. What Maldacena discovered was an exact equivalence, a gravitational theory living inside a volume of that curved space, and a quantum field theory living only on the boundary of that volume were not merely similar. They were not analogous. They were the same theory, written in two different languages. Every event inside the volume, every particle, every gravitational interaction, every curve of space-time had a precise, calculable counterpart on the two-dimensional surface surrounding it. This is what physicists call ADS/CFT correspondence. And it is not a metaphor. It is not an approximation. It is an exact mathematical duality, verified in thousands of calculations across decades of work. What it means, in the quietest possible terms, is this: a universe with gravity and depth and three-dimensional structure can be completely, perfectly described by information living on a flat surface with no gravity at all. The interior is real. The boundary is real. And they are, in some deep sense, the same reality. Resting with that, the depth you feel around you, the space between things, may not be the most fundamental layer of what exists. There may be something thinner, something flatter, something more like a surface from which all of that depth is somehow derived. This is not a comfortable thought. It is not meant to be. But it is, as far as anyone can tell, mathematically true. And it opens a door. If information can generate the appearance of depth and dimension, if a boundary can encode a volume, then the question of what substrate that information runs on becomes, quietly, urgent. One person who took that question seriously, not as a physicist, but as a mathematician and cosmologist, was Max Tegmark. Tegmark looked at the unreasonable effectiveness of mathematics in describing physical reality, a phrase borrowed from the physicist Eugene Wigner, who noticed, decades earlier, that mathematics developed for purely abstract reasons kept turning out to describe the physical world with uncanny precision. Tegmark asked why, and his answer was radical in its simplicity. Perhaps mathematics describes the universe so well because the universe is not described by mathematics, but as mathematics. Not a physical system that happens to obey mathematical laws, but a mathematical structure that simply exists. The way numbers exist, the way geometric relationships exist, without needing a substrate, without needing a cause, without needing anything outside itself. This is the mathematical universe hypothesis. It proposes that every mathematically consistent structure has physical existence, not potential existence, not metaphorical existence, actual existence, somewhere in the same sense that our universe exists. Our universe, under this view, is one structure among an infinite collection of structures, all equally real, all quietly existing in the space of mathematical possibility. Tegmark organized this idea into a hierarchy, 4 levels of multiverse, each more expansive than the last. The first level contains regions of space beyond our observable horizon, places the light from the beginning of time has not yet reached. They exist under standard cosmology, and they are almost certainly real. The second level contains universes with different physical constants, different laws, different fundamental parameters. The kind of variation that inflationary cosmology suggests may have occurred. The third level is the many worlds branching of quantum mechanics. Every outcome of every measurement, quietly occurring in parallel. And the fourth level, the most expansive, the most abstract, the one that contains all the others, is the mathematical universe itself. Every consistent structure, every possible set of axioms, every geometry that does not contradict itself, existing somewhere in the vast and silent space of what mathematics permits. Our universe is one room in an infinite library of rooms, each one a different set of rules, each one fully real. Breathing slowly now. There is no need to hold all of this at once. Let it settle at the edges. Tegmark's hypothesis is not physics in the conventional sense. It makes predictions that are, at present, nearly impossible to test. But it is not empty, either. It is a serious attempt to answer a question that physics alone cannot answer. Why does anything exist at all? And why does it obey rules? And it connects, quietly, to a broader research program that has been developing for decades. Digital physics. The name is simple, almost too simple. It refers to the collection of ideas, proposals, and formal frameworks that explore whether the universe is, at its deepest level, computational, not metaphorically computational, not organized in ways that resemble computation, but actually, fundamentally, running on something like a discrete process, updating according to rules, producing what we experience as reality the way a calculation produces a result. The idea has roots that go back further than most people realize. As early as 1969, a German engineer and computer pioneer named Konrad Zuse proposed that the universe might be running on a discrete computational substrate. He called it Rechnender Raum, computing space. It was not taken seriously at the time. The tools to think carefully about it did not yet exist. But the idea did not disappear. Edward Fredkin, working through the 1970s and 1980s, developed it further. He proposed that the universe might be a finite state machine, updating its configuration step by step according to fixed rules, the way a simple automaton updates its cells. And then Stephen Wolfram, in a long and careful book published in 2002, argued that simple computational rules no more complex than a few lines of code, could, given enough time and space, generate structures of arbitrary complexity, structures that looked, from the outside, like physics. These were not fringe ideas, exactly, but they were not mainstream physics, either. They lived in a productive middle space, taken seriously enough to be argued with, not seriously enough to reshape the field. What changed, slowly, was the mathematics. The holographic principle, AD/CFT, the discovery that quantum error correction codes have a geometric structure that mirrors the curvature of space-time, the growing sense, among some physicists, that entanglement is not just a feature of quantum systems, but a building material of space itself. These results did not prove digital physics. They did not confirm that the universe is a computation, but they made the question harder to dismiss. Because a universe in which information is fundamental, in which the geometry of space is a consequence of how quantum information is organized, in which a three-dimensional volume is exactly equivalent to a two-dimensional boundary, is a universe that has, at minimum, a great deal in common with a computed one. The gaps remain. The questions remain. The places where the analogy breaks down remain. But the picture has grown more detailed, more precise, more difficult to wave away. And so the question rests here, for now, not answered, not abandoned, held gently in the space between what is known and what is only, quietly, possible. The room around you is still. The darkness is soft. And somewhere, in the deep structure of what exists, information is doing something. Something that produces, among other things, this moment, this breath, this slow and gentle dissolving into sleep. There were people thinking about this long before it became a topic of late-night conversation. Konrad Zuse was one of them. Zuse was a German engineer who, in the 1940s, built some of the earliest programmable computers, machines made of metal and wire, involving patient, careful thought. And by 1969, he had arrived at a quiet and remarkable idea that the universe itself might be running on something like what he had spent his life building, a discrete computational substrate processing the world one step at a time. He called it Rechnender computing space. It was not a polished theory. It was more like a question held up to the light. What if the laws of physics are not just describable by computation, but are computation? What if the universe is not merely like a machine, but is one? That question did not disappear. Edward Fredkin picked it up. Fredkin was an American physicist and computer scientist who spent much of the 1980s developing a specific version of this idea. He proposed that beneath the known laws of physics, there might be something even more fundamental, a finite state machine, a system that takes in a state, applies a rule, and produces the next state, over and over, without remainder, without exception. A finite state machine has no memory of anything beyond its current configuration. It does not look ahead. It does not deliberate. It simply transforms what is into what comes next, according to a fixed and unchanging rule. Fredkin believed something like this might underlie physical law itself, not as a metaphor, as a literal description of what is happening at the deepest level of reality. The idea was difficult to formalize, difficult to test, and it attracted as much skepticism as it did curiosity. But it planted something, a way of thinking about the universe not as a collection of particles and forces, but as a process, an ongoing computation whose output, at the scale we inhabit, looks like matter, energy, space, and time. Then came Stephen Wolfram. Wolfram had been a prodigy in theoretical physics before turning his attention to computation, and in 2002 he published a long, dense, and deeply unconventional book called A New Kind of Science. In it, he argued something that many found either profound or overreaching, depending on their disposition. He argued that simple computational rules, applied repeatedly, could generate all the complexity of the physical world. Not approximately, not as a rough sketch, but fully, precisely, completely. His evidence came largely from cellular automata, simple grids of cells, each one either on or off, each one updating its state based on the states of its neighbors, according to a rule that could be written down in a single line. And some of those rules produced something extraordinary. Rule 110 is one of them. It is, on its face, almost absurdly simple. A one-dimensional row of cells, each black or white, each updating according to a pattern that fits in a small table. And yet Rule 110 is capable of universal computation. Given the right initial conditions, it can simulate any computation that any computer can perform. It can, in principle, simulate a mind or a universe. From almost nothing. From a rule simple enough to hold in one thought, complexity without apparent limit. Wolfram saw in this a kind of mirror held up to nature. He believed that the universe might itself be running on something like a cellular automaton, that the apparent smoothness of space, the apparent continuity of physical law, might be the emergent surface of something far more granular and simple underneath. Not everyone agreed. Many physicists found the argument too broad, too loosely connected to the specific mathematical structures that physics actually uses. The book was debated, criticized, and in some quarters dismissed. But the question it raised did not go away. Because there is something in the structure of physics that keeps gesturing in this direction. Consider the speed of light. It is, as far as anyone has ever been able to determine, an absolute ceiling. No signal has ever been observed to travel faster than light in a vacuum. No cause has ever been shown to produce an effect faster than light could carry the information between them. Every experiment, every observation, every measurement has confirmed it. The ceiling holds. In physics, this is usually described as a consequence of relativity, of the geometry of space-time, of the way that space and time are woven together into a single fabric that has its own internal logic. But there is another way to describe it. A processor has a clock rate, a maximum speed at which it can perform operations. Information cannot move through the system faster than the clock allows, not because something is blocking it, but because the system simply does not update faster than that. The speed of light functions, in this analogy, as the clock rate of the universe. Not a wall that things run into, but a limit built into the substrate itself, a consequence of how the underlying system processes and propagates information. This is not a proof of anything. It is an analogy, and analogies can mislead as easily as they illuminate. But it is the kind of analogy that is difficult to set aside entirely, because it fits so cleanly. Because the speed of light is not just a speed, it is a universal constant that appears in equations describing electromagnetism, gravity, quantum mechanics, thermodynamics. It is woven through the laws of physics in a way that suggests it is not incidental, but foundational. And if it is foundational, if it is a property of the substrate rather than a property of the things moving through the substrate, then the substrate begins to look less like empty space and more like something that processes, something that has a rate, something that, in some deep and not yet understood sense, computes. The night is quiet around you now. These ideas have a way of expanding when you follow them, each one opening into another, each answer revealing a deeper question. Zeus with his computing space, Fredkin with his finite state machine, Wolfram with his simple rules and their inexhaustible complexity. And beneath all of it, the speed of light, holding steady, never exceeded, never explained away. None of this is settled. None of it is close to settled. The physicists who find these ideas compelling are a minority, and even among them, there is little agreement about what form a computational universe would actually take, or how one would go about confirming it. But the conversation has been happening for a long time now, longer than most people realize, carried forward by careful thinkers who were willing to ask whether the universe might be, at its root, something more like a process than a place. Something that runs, something that updates, something that produces, from simple rules applied in sequence, the full and intricate texture of everything that exists, including this room, this darkness, this slow and steady rhythm of your breathing. You do not need to hold any of this tightly. Let it rest where it is, somewhere at the edge of thought, where the questions are still open and the night is still soft. The ideas will be here when you return to them. For now, there is only the quiet and the gentle, unhurried work of sleep. And yet, even as that thought settles, there is another layer waiting beneath it, one that does not come from philosophy or from the long tradition of thinkers asking whether the world is real. It comes from physics itself, from the equations that have been tested more carefully than almost anything else in the history of science. And what those equations say, quietly, without drama, is that the world at its smallest scale is not smooth. It is not continuous. It is granular, broken into pieces that cannot be broken further. This is not a metaphor. It is one of the most precisely confirmed facts in all of science. And it begins, as so many things do, with someone trying to solve a problem that seemed, at the time, entirely mundane. In the year 1900, a physicist named Max Planck was working on a puzzle involving light and heat. Specifically, he was trying to understand why hot objects glow the way they do. Why a piece of iron, heated slowly, shifts from dull red to bright orange to something approaching white. The equations of the time predicted something that could not possibly be right. They predicted that a hot object should radiate infinite energy at short wavelengths. An infinite amount of energy pouring out of something as ordinary as a warm stove. This was called the ultraviolet catastrophe. Not because it was dramatic, but because the mathematics broke down precisely in the ultraviolet range of light. Planck found a way to fix the equations. But the fix required something strange. It required assuming that energy does not flow in a smooth, continuous stream. It comes in packets, discrete, indivisible units. He called them quanta, and he was, by his own account, deeply uncomfortable with what he had done. He thought of it as a mathematical trick, a temporary patch on a leaky theory. He did not fully believe, at first, that the quanta were real. But they were. They are. Energy does not come in any amount you like. It comes in steps. Whole numbers of a fundamental unit, never fractions, never in between. And it is not only energy. Spin comes in discrete units. Electric charge comes in discrete units. The deeper you look into the fabric of the physical world, the more you find that it is made of things that cannot be subdivided. Minimum amounts, irreducible pieces, the kind of structure you might expect to find if something were being counted rather than measured. If something were being processed rather than simply existing. This is worth sitting with for a moment. Not rushing past. The universe, as far as we can tell, does not permit infinitely fine gradations. There is a smallest unit of action, a smallest meaningful distinction. And below that threshold, the question of what is happening may not have an answer. But the discreteness of energy is only the beginning. Because quantum mechanics does something else. Something that has no parallel in the world of ordinary experience. It ties the behavior of matter to the act of observation. This is not a poetic statement. It is a description of what the experiments show. The double-slit experiment is perhaps the clearest demonstration. A particle, an electron, say, or a photon, is fired toward a barrier with two narrow openings. On the far side of the barrier is a screen that records where the particle lands. When no one measures which slit the particle passes through, the pattern that builds up on the screen is an interference pattern. Bands of light and dark, the signature of a wave passing through both openings at once and interfering with itself. But when a detector is placed at the slits, when the path of the particle is recorded, the interference pattern disappears. The particle behaves as though it passed through one slit or the other, not both. The act of gathering information about the particle's path changes what the particle does. This is not a disturbance caused by clumsy instruments. The effect persists even when the measurement is made with the most delicate possible means. It is not about the physical intrusion of a detector. It is about whether information exists. Whether the path is, in principle, knowable. If it is knowable, the interference vanishes. If it is not, the interference remains. There is no classical analog for this. Nothing in the world of large objects, of stones and rivers, and turning wheels behaves this way. A stone does not change its trajectory because someone looked at it. But a particle does. Or rather, and this is the careful way to say it, the probability distribution describing where a particle might be found changes depending on whether information about it has been recorded. This is what physicists call wave function collapse. Before a measurement, a particle exists in a superposition, a kind of weighted cloud of possibilities, each with its own probability. It is not that the particle is in one place and we simply do not know which. The mathematics and the experiments suggest something stranger, that the definite outcome does not exist until the measurement is made, until information is, in some sense, registered. The wave function, the mathematical object that encodes all the possibilities, transitions from a spread of potential states to a single, definite one. And that transition is called collapse. What causes it, exactly, is one of the deepest open questions in physics. Some interpretations place the observer at the center of the story. Not a human observer, necessarily, but any physical process that records information, any interaction that leaves a trace. Under these interpretations, reality does not become definite until something, somewhere, takes note of it. Until the information is, in some sense, written down. This is not a fringe position. It is one of several serious, carefully developed frameworks for understanding what quantum mechanics is actually telling us about the world. And it carries a quiet implication that is difficult to ignore. If reality only crystallizes into definite form when information is recorded, if the act of measurement is not incidental to the story but somehow central to it, then information is not just a description of the world. It may be something closer to the world's foundation. This is where the threads begin to draw together. The discreteness that Planck found in energy, the observer dependence that the double-slit experiment reveals, the way the wave function holds all possibilities open until something registers a definite outcome. None of these facts, on their own, prove that the universe is a computation. They do not prove anything of the sort, but they share a texture, a quality that feels, to some physicists and philosophers, less like the texture of a continuous, self-existing physical world, and more like the texture of something that is being processed, something that resolves its states only when it needs to, something that holds uncertainty in suspension until a record is made. The resemblance may be coincidence. It may be a projection, a human tendency to see familiar patterns in unfamiliar places. That possibility deserves to be taken seriously. The mind that has built computers will naturally reach for computational metaphors when it encounters discreteness and observer dependence. That does not mean the metaphors are wrong, but it does mean they should be held gently, as possibilities, as questions still open in the dark. The equations are real. The experiments are real. What they mean, what they are pointing toward, if they are pointing toward anything at all, remains, for now, beautifully, quietly unresolved. And that is all right. You do not need to resolve it tonight. Let the questions float. Let the wave function of your own thoughts spread out softly into all its possibilities. There is no measurement being made here, no record being taken, only the slow, unhurried drift towards sleep. There is one interpretation of quantum mechanics that takes a different path entirely. Rather than accepting that possibilities collapse into a single outcome, it asks a quieter question. What if nothing collapses at all? What if every outcome simply continues? This is the many-worlds interpretation proposed by Hugh Everett in 1957, and it suggests that when a particle faces a fork, spin up or spin down, here or there, the universe does not choose. It branches. Both outcomes occur, each in its own thread of history, each as real as the other. There is no collapse, no single answer selected from the possibilities, only a vast, silent proliferation of worlds, each one unaware of the others, each one carrying forward its own version of events. In this picture, the universe is something like an enormous tree. Not a tree that grows upward toward light, but one that branches inward and outward and in every direction at once, at every moment, for every particle, for every interaction that has ever taken place since the beginning of time. The number of branches is not merely large, it is a number that has no comfortable home in ordinary language, and yet the mathematics is clean. The equations do not require collapse. They do not require a special role for observers. They simply evolve, smoothly and continuously, branching as they go. Some physicists find this deeply satisfying. The theory is, in a certain sense, the most literal reading of the equations. Take them seriously. It says, let them mean what they say. Others find it extravagant. The cost of avoiding collapse is an infinity of unobservable worlds, and some argue that is too high a price for tidiness. But there is something worth sitting with here. If the many worlds interpretation is correct, then the universe is, at its deepest level, a computational structure, a tree of all possible measurement outcomes, branching without end, every path taken, every path not taken, all of it, somewhere, real. That is a thought that does not need to be grasped tonight, only noticed, and set gently aside. There is another thread worth following, one that connects quantum mechanics to the fabric of space itself. In quantum computing, researchers work with something called quantum error correction. It is a way of protecting fragile quantum information from the noise and disturbance that would otherwise destroy it. The codes used to do this have a particular mathematical structure, and in recent years, physicists have noticed something unexpected. That structure mirrors aspects of space-time geometry. The way information is distributed across a quantum error correcting code, the way it is spread out so that no single piece holds the whole, resembles, in precise mathematical terms, the way geometry emerges in certain theories of gravity. This is not a loose analogy. It is a structural correspondence. The same equations appear in both places, and that kind of coincidence, in physics, tends to mean something. It has led some researchers to ask a question that would have seemed strange not long ago. What if space-time is not the stage on which quantum mechanics plays out, but something that quantum mechanics builds? Physicist Mark van Ramsdonk explored this idea carefully. He and others have proposed that the geometry of space, the distances between things, the curvature that we experience as gravity, may emerge from quantum entanglement. Entanglement is the phenomenon in which two particles share a quantum state, so that measuring one instantly affects what can be known about the other, regardless of the distance between them. Einstein called it spooky action at a distance, and spent years hoping it would turn out to be an illusion. It is not an illusion. And the proposal now is that entanglement is not just a strange feature of quantum systems, but a structural ingredient of space itself. When two regions of space are connected, when there is a path between them, a geometry linking them, that connection appears to correspond to the degree of entanglement between the quantum degrees of freedom in those regions. More entanglement, more connection, more geometry. Less entanglement, and the regions begin, in a mathematical sense, to pull apart. This is sometimes expressed in the phrase ER equals EPR, a shorthand for the idea that the geometric bridges of general relativity and the entanglement correlations of quantum mechanics may be, at some deep level, the same thing. It is a hypothesis, not a settled theory, but it is taken seriously by serious people, and it points towards something quietly remarkable. That space, the seemingly empty, continuous, self-evident backdrop of all experience, may be woven from something more fundamental, from relationships, from correlations, from the quiet threading of one part of reality to another through quantum connection. If that is true, then space is not a container, it is a consequence. And that changes the picture considerably. Now, there is a difficulty that runs beneath all of this. A difficulty that becomes important when the simulation hypothesis is considered carefully. Simulating quantum systems is extraordinarily hard. Not hard in the way that a difficult calculation is hard, but hard in a way that grows without bound. When you try to simulate a quantum system on a classical computer, a system of particles that can be entangled, that can exist in superpositions, the resources required do not grow in proportion to the number of particles. They grow exponentially. Add one more particle to the system, and the computational cost roughly doubles. Add 10 more, and it multiplies by a factor of roughly 1,000. Add 100 more, and the number of operations required exceeds, by an enormous margin, anything a classical machine could perform in the lifetime of the universe. This is not a limitation of current technology. It is a feature of the mathematics itself. The space of quantum states is vast beyond any classical description, and to track it faithfully requires resources that scale in a way that quickly becomes unimaginable. This is, in fact, precisely why quantum computers are being built. A quantum system, it turns out, can simulate another quantum system efficiently because it speaks the same language. It does not need to translate quantum behavior into classical bits. It simply is quantum. But for a hypothetical simulator running our universe, a universe of roughly 10 to the 80 particles, all of them, quantum, all of them entangled in ways we are only beginning to map, the computational cost would be something that resists even the most expansive imagination. Some physicists point to this as a serious objection to the simulation hypothesis, not a refutation, but a weight on the scale. The resources required would not merely be large, they would need to be, in some sense, larger than the universe itself, which raises the question of what it would even mean for such a simulator to exist. Others respond that a sufficiently advanced civilization might find ways around this. Perhaps the simulation does not need to track every particle faithfully at all times. Perhaps it uses approximations. Perhaps it only resolves the details of regions that are, in some sense, being examined. These are possibilities. They cannot be ruled out, but they cannot be confirmed either. And so the question rests here, for now, in the space between what the mathematics demands and what imagination can reach. The universe, as far as we can tell, is quantum all the way down. Its states are vast, its entanglements are deep, and the cost of representing it faithfully grows in a way that quietly resists the simulation picture. Or perhaps it points towards something stranger still. Perhaps the universe is not being simulated from outside. Perhaps it is, in some sense, computing itself, processing its own states, building its own geometry from the entanglement of its own parts. That thought does not need an answer tonight. Let it rest where it is, somewhere between the question and the quiet. And this is part of why quantum computers are being built at all. Classical machines, the kind built from ordinary transistors, processing ordinary bits cannot efficiently simulate quantum systems. The mathematics simply does not cooperate. As the number of particles grows, the computational cost does not grow alongside it in a manageable way. It grows exponentially. Each additional particle roughly doubles the information needed to track the whole system. A few hundred particles, fully entangled, would require more classical bits to describe than there are atoms in the observable universe. So we build machines that are themselves quantum, that hold superpositions, that process entanglement with entanglement. It is, in a quiet way, a remarkable thing. We are constructing tools whose only hope of describing nature is to become, in some small measure, like nature. And yet, even quantum computers have limits. They are fragile. They require temperatures colder than deep space to function. They decohere, lose their quantum character at the slightest disturbance. We are still, in many ways, at the very beginning of understanding what they can and cannot do. But hold that thought for a moment. If the universe is a simulation, then whatever is running it faces this same problem, only incomparably larger. Not a few hundred particles, not a few billion. Every particle in every galaxy across a volume of space roughly 93 billion light-years wide. Every quantum state, every entanglement, every superposition held and updated and resolved at every moment. The computational resources required would dwarf anything we can currently conceive of. Not by a little, by a margin so vast it resists ordinary description. We do not have language that comfortably holds numbers that large. We can write them down in scientific notation on a page, but the scale does not land the way it should. It simply exceeds the reach of intuition. Some researchers look at this and conclude that the simulation hypothesis, whatever its philosophical appeal, is physically implausible. Not because the idea is incoherent, but because the cost is, as far as we can tell, genuinely prohibitive. Even a civilization of unimaginable sophistication would be constrained by the laws of physics. Information cannot be processed faster than certain limits allow. Energy cannot be conjured from nothing. The universe, if it is a computation, is an extraordinarily expensive one. This is not a dismissal. It is a constraint. And constraints matter in science. But others respond to this constraint differently. They point out that the argument assumes the simulation must be faithful, that it must track every particle in every unobserved corner of the cosmos at all times. And perhaps it does not have to. Perhaps a sufficiently advanced civilization would not simulate the entire universe in full resolution continuously. Perhaps it would use approximations. Perhaps it would only resolve the fine structure of regions that are, in some sense, being examined, leaving the rest in a kind of compressed, lower resolution state, waiting. This idea has a name. In some discussions, it is sometimes called lazy rendering. The phrase comes from the world of computing. In certain systems, calculations are deferred until their results are actually needed. Nothing is worked out in advance if it does not have to be. The computation happens on demand, and only then, and there is a more visual version of the same idea. In the rendering of three-dimensional environments, the kind built for interactive simulations, where a participant moves through a constructed space, there is a long-established technique. The system does not draw what the participant cannot see. Surfaces behind walls, regions beyond the horizon, details too distant to resolve. These are not rendered. They are, in a sense, not yet real. They exist as potential, as data waiting to be called upon, and they become fully present only when the viewpoint shifts toward them. It is an efficient approach, It allows vast environments to exist without the cost of computing every corner of them at every moment. Some who take the simulation hypothesis seriously find this suggestive. They note that quantum mechanics has something that looks, at least superficially, like this quality. A particle in superposition does not have a definite position, a definite spin, a definite state. It holds multiple possibilities at once. And when a measurement is made, when the system interacts with something that records information about it, a definite outcome appears. The superposition resolves. Whether this resemblance means anything is genuinely unclear. The analogy is evocative, but analogy is not argument. Quantum superposition arises from the mathematics of wave functions and probability amplitudes. It is not, as far as anyone has demonstrated, a sign that the universe is conserving computational resources by deferring calculations. Still, the parallel is there, and it is the kind of parallel that is difficult to entirely set aside. There is something almost restful about the lazy rendering picture, if you let yourself sit with it. The idea that most of the universe, at most moments, exists in a kind of patient suspension, not absent, not false, but not yet fully resolved, waiting for something to look, to interact, to ask a question of it. It is not so different, in a way, from how memory works. The past does not exist in full detail in the mind. It exists as a compressed trace, reconstructed when needed, filled in with inference and pattern. We do not carry the complete record of every moment. We carry enough to rebuild something close to it. When the occasion calls, perhaps the universe is more like that than we tend to assume. Or perhaps not. Perhaps the universe is fully real in every corner, at every scale, at every moment. And the simulation picture is simply a story we tell because our own tools for building environments happen to use these tricks, and we cannot help but project them outward. That is worth holding to. The simulation hypothesis is, in part, a mirror. It reflects the technology of the moment that produces it. Earlier centuries imagined the cosmos as a great clockwork because clocks were the most intricate machines they knew. Later, it became a vast engine, then a telephone exchange, then a computer. Now, in an age of rendered environments and quantum processors, it becomes a simulation. Each metaphor captures something, and each one also imports assumptions that may not belong. This does not make the question unimportant. It makes it worth approaching slowly, with care, without rushing toward a conclusion that the evidence does not yet support. What we can say, quietly and with some confidence, is this: the universe behaves as though information matters, as though the act of measurement is not passive but participatory, as though the boundary between observer and observed is not as clean as it once seemed. These are not small things. They are strange, and they are real, and they have been confirmed in laboratories many times over. Whether they point toward a simulation or toward something else entirely, something we do not yet have the concepts to name, remains open. And open questions, held gently, are not a source of unease. They are simply the shape of the horizon, always there, always a little further than the last step. You do not need to resolve this tonight. The question has been sitting here, in one form or another, for a very long time. It will still be here tomorrow, patient, quiet, asking nothing of you right now. Let the numbers go, the exponentials, the lattices, the rendered edges of things. Let the universe be whatever it is, and let yourself be still inside it. There is a kind of light that has been traveling toward you for almost 14 billion years. It did not begin as light, exactly. It began as heat, the afterglow of a universe so young and so dense that matter and energy had not yet learned to separate. And then, about 380,000 years after the beginning, the universe cooled just enough, and the light was released, free to travel in every direction at once, forever. We call it the cosmic microwave background. It fills the sky in every direction, almost perfectly uniform, almost perfectly smooth. If you could see it with your eyes, it would look like a faint, even glow, the same in every direction, the same temperature everywhere to within about 1 part in 100,000. And yet, not perfectly smooth. There are fluctuations, tiny wrinkles in that ancient light. Variations so small, they are almost nothing, and yet they are everything. Because those wrinkles, those faint ripples in the temperature of the early universe, are the seeds from which all structure grew. Every galaxy, every cluster of galaxies, every filament of matter stretching across hundreds of millions of light years, all of it traces back to those quiet, almost imperceptible variations in the first light. The universe we live in grew from almost nothing, from the faintest whisper of unevenness in an otherwise featureless glow. What is remarkable, and this is worth sitting with for a moment, is that those fluctuations are not random in the way a spilled glass of water is random. They follow a pattern, a precise statistical distribution called a nearly scale invariant power spectrum, which means the fluctuations appear at roughly the same strength across a very wide range of scales, small scales and large scales, close and far, all carrying variations of similar magnitude. This is not what you would expect from pure noise. Pure noise has a shape, and this is a different shape. A shape that suggests something structured the early universe at a very deep level, something that set the initial conditions with a kind of mathematical regularity. Cosmologists have a model for this: inflation, a period of extraordinarily rapid expansion in the universe's first moments, and that model predicts this pattern quite well. But the pattern itself, the near-perfect scale invariance, has struck some researchers as the kind of thing that might also emerge from something else. From a computational process, for instance, if the universe were running on some kind of discrete substrate, a lattice, a grid, a set of rules being applied step by step, you might expect the initial conditions to carry the signature of that substrate. You might expect the fluctuations to be not quite random, but structured in a way that reflects the underlying architecture. And so, some researchers have looked carefully, methodically, without expectation. They have examined the cosmic microwave background for signs of unexpected regularities, for cutoffs at particular scales, for patterns that would be difficult to explain by known physics, but might make sense if the universe were, at some level, computed. So far, nothing confirmed has been found. The CMB looks, as best as current instruments can tell, like what the standard model of cosmology predicts. The fluctuations are there, and they are beautiful in their precision, but they do not yet carry any unmistakable fingerprint of a computational grid. The search continues, in various forms, as instruments improve and analysis methods grow more refined. But for now, the ancient light offers no clear answer. It simply glows, patient and even carrying its almost uniform warmth across the whole sky. There is another place researchers have looked, though, a different kind of signal, arriving not from the early universe, but from the most energetic corners of the present one. Cosmic rays. These are not rays in the way light is a ray. They are particles, protons, atomic nuclei, occasionally something heavier, accelerated to extraordinary energies by processes we do not fully understand. Supernovae, perhaps, or the violent regions near black holes, and they travel across vast distances before arriving, quietly and continuously, at the upper edges of our atmosphere. Most cosmic rays arrive with a wide range of energies, but there is a known upper limit, a ceiling beyond which very few particles are observed. This is called the GZK cutoff, after the physicists who predicted it, and it arises because particles traveling at extreme energies interact with the cosmic microwave background itself, losing energy over long distances. In 2012, a physicist named Silas Bean, along with colleagues, published a paper that asked a quiet but pointed question. If the universe were being simulated on a discrete lattice, a computational grid with a finite spacing, the way a digital image is made of pixels, would that lattice leave a detectable signature in the cosmic ray spectrum? Their answer was, possibly. A lattice has preferred directions, axes along which the grid is aligned, and particles traveling along those axes would behave slightly differently from particles traveling at angles to them. The lattice would, in a sense, have a grain, the way wood has a grain, and that grain would introduce a subtle anisotropy, a directionality, into the highest energy cosmic rays. More than that, the lattice spacing would impose a hard upper limit on particle energy, not the GZK cutoff, which has a known physical cause, but a different cutoff, one that could not be explained by interactions with background radiation, one that would simply be the edge of what the computational substrate could represent. The paper was careful. It did not claim the universe is a simulation. It asked whether, if it were, we might be able to tell. And it suggested that the answer might be yes, that the highest energy cosmic rays could, in principle, carry the imprint of a computational grid. If one exists, this is the kind of science that sits at the very edge of what science can currently do. It is not speculation dressed as research. It is a genuine attempt to ask, what would we look for? And where would we look? The answer, for now, is that we have not found it. The cosmic ray spectrum does not yet show a clear lattice signature. The cutoffs and anisotropies that would confirm a computational substrate have not appeared in the data. But the data is limited. The highest energy cosmic rays are rare, and detecting them requires enormous instruments spread across wide areas of ground. The statistics are thin at the extreme end of the energy spectrum, and thin statistics leave room for uncertainty. So the question remains open. Not dramatically open, not urgently open, just quietly, persistently open. The way many questions in physics remain open for decades before the instruments catch up to the ideas. There is something almost tender about this kind of science, the act of looking at the oldest light in the universe, or at the most energetic particles crossing the sky, and asking, gently, whether any of it carries a message about the nature of what we are inside of. Not demanding an answer, not insisting on one, just looking carefully with the best tools available and noting what is found and what is not. The universe does not seem to mind being examined this way. It continues to glow and to rain particles and to expand in all directions at once, indifferent to the question being asked of it. And perhaps that is the right posture to take with all of this. Not urgency, not anxiety, not the need to know tonight, just a quiet willingness to look. And to rest, for now, in the not yet knowing. The ancient light is still out there, in every direction, even above you, even now, traveling, as it has always traveled, without hurry, without destination. Let it be there, and let yourself be here. There is a question that sits beneath all of this. Not the question of whether a simulation could be built, or whether the mathematics of space-time hints at something computational, but a quieter, more fundamental question. Could we ever know? And the honest answer, as far as anyone can tell, is that we probably could not. Not with certainty, not in any way that would settle the matter the way an experiment settles a matter in a laboratory. This is what philosophers and scientists call the falsifiability problem, and it is, in some ways, the deepest difficulty the simulation hypothesis faces. A hypothesis is falsifiable when you can describe it in advance. What evidence would prove it wrong? You make a prediction. You look. If the prediction fails, the hypothesis fails with it. That is the engine of science, the method that separates a testable claim from a story. Karl Popper, the philosopher of science, made this the cornerstone of his thinking in the 20th century. His criterion was simple and demanding. A claim must be testable to qualify as scientific, not merely plausible, not merely coherent. Testable, capable of being wrong in a way that could be observed. And the simulation hypothesis, for all its mathematical texture and philosophical depth, struggles here. It is very difficult to describe what evidence would rule it out. If the universe is a simulation, it might be designed to look exactly like a non-simulated universe. Every test we run, every particle we measure, every ancient photon we catch in a detector, all of it could be the output of a process we have no access to. The simulation, if it exists, contains our instruments. It contains our mathematics. It contains the very reasoning we would use to investigate it. This is not a small problem. It means that the hypothesis, as currently formulated, sits closer to philosophy than to empirical science. That is not a dismissal. Philosophy is not a lesser thing, but it is a different kind of inquiry, one that proceeds by argument and reflection rather than by prediction and measurement. And yet, some philosophers push back gently on the idea that unfalsifiability makes a hypothesis meaningless. A claim can be untestable and still be worth thinking about carefully. It can still be true or false, even if we have no way to determine which. The question of whether there was a moment before the Big Bang is, in a similar way, extremely difficult to test, perhaps impossible with current physics. And yet, it is not a meaningless question. It points at something real about the structure of time and causation. The simulation hypothesis is in this company. It shares its epistemic status, that uncertain, neither confirmed nor refuted position, with some of the most serious ideas in modern physics. Certain interpretations of quantum mechanics, including the many-worlds interpretation, are also not straightforwardly falsifiable. The branching parallel histories that interpretation describes are, by construction, inaccessible to any observer within a single branch. And yet physicists take the interpretation seriously, debate it carefully, and find it illuminating, even without a decisive test. The same is true of multiverse theories more broadly, the regions of space beyond our cosmic horizon. The other bubble universes that some inflationary models predict, these are not observable in any direct sense, and still they are discussed, modeled, and taken as genuine possibilities by careful researchers. The simulation hypothesis lives in this same neighborhood, not proven, not disproven, not currently productive as a research program in the way that, say, dark matter searches are productive, but not empty, either. It asks real questions about the nature of information, the structure of physical law, and the relationship between mathematics and existence. And it has ancestors. Long before anyone thought about computational substrates or Planck scale lattices, philosophers were asking a version of the same question. In 1641, René Descartes sat down to think as carefully as he could about what he could know with certainty. He was not writing science fiction. He was doing rigorous philosophy, trying to find a foundation for knowledge that could not be shaken. And he arrived at a troubling possibility. He imagined a powerful deceiver, an evil demon. He called it with the ability to make all of his sensory experience systematically false. Every sight, every sound, every sensation of his own body, all of it could, in principle, be the fabrication of this demon. The world Descartes thought he inhabited might be entirely constructed, fed to him as experience, while the true nature of things remained hidden. This is not so different from the simulation hypothesis. The demon is, in a sense, the simulator. The constructed experience is, in a sense, the rendered world. Descartes was asking, in the language of his time, whether the reality we perceive could be a kind of elaborate fiction imposed from outside. His response to this was the cogito, the observation that the very act of doubting, the act of thinking, of questioning, proves that something is doing the thinking. Even if everything else is false, the existence of a mind engaged in doubt cannot itself be doubted. That much, at least, is certain. It is a quiet kind of certainty. Not certainty about the world outside, not certainty about the nature of matter or space or time, just the bare, irreducible fact of a thinking thing present to itself in this moment. And there is something almost restful about that. Whatever the universe is made of, whether it is continuous or discrete, whether it is information all the way down, whether it is the output of some process we cannot see, the experience of being here, of noticing, of wandering quietly in the dark, that is not nothing. Descartes could not resolve the demon. He could not prove the deceiver did not exist. He moved past it by other means, through arguments that later philosophers found less convincing than the cogito itself. But the question he raised did not go away. It passed through centuries of philosophy, changing shape as it traveled. It became the brain in a vat scenario, developed by the philosopher Hilary Putnam in the 20th century, a more clinical, more modern version of the same unease. A brain, removed from its body, kept alive in a laboratory, fed electrical signals that produce a complete and convincing experience of a world that is not there. And then it became the simulation hypothesis, grounded now not in demons or laboratories, but in the logic of technological development, in the mathematics of information, in the physics of computation. The question is older than computers, older than quantum mechanics, older than the word simulation itself. It is, at its root, the question of whether the world we find ourselves in is the world as it is, or a world as it is presented to us, shaped by something we cannot step outside of to examine. And the honest answer, the careful answer, is that we do not know. We have not found the seams. We have not found the artifacts. We have found hints that some physicists find suggestive and others find unconvincing. And we have found a hypothesis that is coherent and serious and are, for now, beyond the reach of any test we know how to design. That is where it rests. Not solved, not dismissed, just open, the way certain deep questions remain open, held lightly, examined carefully, and set down again without force. You can set it down now, too. The question will still be there, patient, unhurried, waiting in the same place you left it. And you are here, in whatever this is, thinking, noticing, present. That much is certain. Let that be enough for tonight. There is a philosopher who asked this question long before anyone had a computer to point to. His name was René Descartes, and he asked it in 1641, sitting alone, by firelight, in the middle of winter. He was not asking idly. He wanted to find something he could be certain of, truly certain, the way a stone is solid, the way 2 and 2 make 4, and so he began by asking what he could doubt. And he found he could doubt almost everything. He could doubt his senses, because the senses sometimes deceive. He could doubt the world outside his window, because dreams feel real while they are happening. He could doubt mathematics, because perhaps some powerful deceiver, some vast, invisible intelligence, had arranged things so that even his clearest reasoning led him astray. He called this figure the evil demon. Not a demon in any religious sense, simply a hypothetical, a thought experiment with a very sharp edge. If such a deceiver existed, Descartes asked, what would remain? What could survive even that? And he found one thing: the doubting itself. To be deceived, you must be thinking. To think, you must exist. The act of questioning cannot be performed by nothing. Even if everything else were false, the fire, the room, the winter, the hands holding the pen, the questioning would still be real because something would have to be doing it. That is the cogito. I think, therefore, I am, or more precisely, there is thinking happening, and therefore there is something it is happening in. It is a small island of certainty in a very large sea of doubt, but it is solid, and Descartes built from it carefully. He was not trying to prove the world was fake. He was trying to find what was real. The demon was a tool, not a conclusion. And yet the question he raised, whether experience could be systematically, completely, and undetectably false, did not go away. It came back, centuries later, in a different form. Hilary Putnam, a philosopher working in the latter half of the 20th century, gave it a new shape. He called it the brain in a vat. The scenario is simple to describe. A brain, removed from its body, kept alive in a laboratory, connected by wires to a computer that feeds it a continuous, perfectly consistent stream of sensory experience. The brain believes it is walking, breathing, seeing, touching. It has no way to know that none of this is happening. The signals are indistinguishable from the real thing because the brain has nothing to compare them to. It is Descartes' demon, translated into the language of neuroscience and computation. But Putnam did something unexpected with it. He did not use the scenario to argue that we might be brains in vats. He used it to argue that even if we were, we could not coherently say so. His reasoning was careful and a little strange. When a brain in a vat thinks the word tree, what does that word refer to? It has never encountered a real tree. Every experience it has of trees has been generated by the computer. So the word tree in the brain's vocabulary refers to the simulated version, to the electrical pattern, not the wooden thing rooted in soil. And so when the brain thinks, I might be a brain in a vat, and my experiences might be false, the word false is also drawn from the simulation. The brain has no concept of real that reaches outside the system it is embedded in. Putnam's conclusion was that the sentence, I'm a brain in a vat, cannot be meaningfully true for the brain saying it, because the very language it uses to make the claim is shaped by the simulated world. The claim undermines itself. This is not a proof that we are not in a simulation. It is something quieter than that. It is a reminder that the tools we use to question reality are made of the same material as the reality we are questioning. We cannot step outside the frame to check the frame. Descartes found a floor, the thinking self, and stood on it. Putnam found a ceiling, the limits of reference, and pointed up at it. Both were mapping the same room. The simulation hypothesis, as Bostrom formulated it, is related to these ideas, but it arrives from a different direction. Descartes and Putnam were doing philosophy, asking what we can know, what we can mean, what we can doubt. Bostrom was doing something closer to probability theory. He was not asking whether deception is conceivable. He was asking whether, Given what we know about the trajectory of technology, simulation is likely. That is a different kind of question. It does not rest on an evil demon or a laboratory vat. It rests on the assumption that civilizations, if they survive long enough, will eventually build computers powerful enough to run minds, and that if they do, the number of simulated minds will vastly outnumber the biological ones, and that, therefore, a randomly selected mind, yours, mine, any mind, is probably not among the originals. The philosophical ancestors asked, could this be happening? Bostrom asked, given the numbers, is it not probably happening? That shift from conceivability to probability is what gave the hypothesis its particular texture in the early 21st century. It moved the conversation out of the philosophy seminar and into a different kind of room. A room where engineers and physicists and, eventually, public figures began to weigh in. Some of those public figures spoke with considerable confidence. Elon Musk, among others, stated publicly that he considered the probability of living in base reality, in the original, uncomputed world, to be very low. He put the odds of not being in a simulation at something like 1 in billions. It is worth saying clearly, this is not a scientific claim. It is not based on a calculation, or a measurement, or a peer-reviewed argument. It is an intuition expressed by someone with a large platform about a question that remains genuinely open. The statement spread widely, as such statements do. And it did something interesting to the conversation. It made the hypothesis feel urgent, almost settled, in a way that the careful philosophical and scientific literature does not support. Physicists who work on related questions, on digital spacetime, on the holographic principle, on the computational structure of quantum mechanics, tend to be much more measured. They find the hypothesis interesting, worth thinking about, possibly connected to real physics, but not confirmed, not even close to confirmed, and perhaps not confirmable at all. The gap between that careful uncertainty and the confident public pronouncements is worth noticing. Not to dismiss the question is real and serious and old, but to hold it the way it deserves to be held, lightly, with open hands, without forcing it toward a conclusion it has not yet earned. Descartes sat with his doubt by the fire and found one solid thing. Putnam traced the edges of what language can reach and found a boundary. Bostrom counted minds and found a probability. And the question is still here. Patient. Unchanged. Resting in the same place it has always rested, at the edge of what we can know about the nature of the world we find ourselves in. You are still here too, breathing slowly. The thinking still happening, quietly, the way it does. That much has not changed. And yet the physicists themselves, the ones who spend their days working on the actual mathematics of space-time, of information, of quantum structure, most of them set the simulation hypothesis to one side, not with contempt. With something more like patience. They find it worth a thought, worth an hour of conversation, perhaps worth a paper at the edges of their field, but not worth reorganizing a research program around. Not yet, possibly not ever. The hypothesis does not currently generate predictions that differ from ordinary physics in ways that could be tested, and without that, it remains a philosophical position dressed in the language of science. Interesting, but not productive in the way that science needs its questions to be productive. That is not a dismissal. It is a description of where the question lives. And where it lives is close to another question, one that may be even harder, one that the simulation argument quietly depends on. The way a building depends on its foundation. The question of consciousness. Because the entire structure of Bostrom's argument rests on an assumption that a mind can run on something other than a biological brain, that the particular arrangement of neurons and synapses and electrochemical signals that gives rise to your experience right now is not the only possible arrangement, that experience itself is, in some sense, substrate independent. If that assumption is wrong, if consciousness is tied irreducibly to the specific physical processes of living tissue, then simulated minds are not possible, and the argument dissolves before it begins. But if the assumption is right, if experience can arise from any sufficiently organized system, regardless of what it is made of, then the question opens very wide. There is a theory that tries to say something precise about this. It is called integrated information theory, and it was developed by the neuroscientist Giulio Tononi. The theory proposes that consciousness is not a special substance, not a mysterious addition to the physical world. It is a property, a measurable property, of how information is organized within a system. The key idea is integration. A system is conscious, under this theory, to the degree that its parts share information with each other in a way that cannot be reduced to the sum of those parts working separately. The more tightly integrated the information flow, the higher the degree of what Tononi calls phi, and the richer the experience. A simple light switch has almost no integration. Its states are too few, too isolated. Whatever phi it has is vanishingly small. But a human brain, with its 100 billion neurons, each connected to thousands of others, each influencing and being influenced by the whole, its phi, under this framework, would be very large. And here is where it touches the simulation question. Under integrated information theory, a sufficiently complex computational system, one with the right kind of internal structure, the right degree of integration, could, in principle, have phi, could, in principle, be conscious, not because it is made of neurons, but because of how its information is organized. That is a significant claim. It means that the substrate might not be what matters. The pattern might be what matters. The way information flows and folds back on itself and integrates into something unified. If that is true, then a mind running inside a simulation would not merely be processing information, it would be experiencing. There would be something it is like to be that mind, a felt quality to its existence. The same kind of felt quality that is present right now. As you rest here, as the room holds, it's quiet around you. But integrated information theory is not settled science. It is a serious proposal, developed with mathematical rigor, taken seriously by many researchers, and contested by many others. Some argue that its definition of integration is too broad, that it would attribute consciousness to systems that seem clearly not conscious. Others argue that it is too narrow, that it misses something essential about the biological basis of experience. The debate is ongoing and careful, and beneath all of it, beneath every theory of consciousness, every framework and model and proposal, there is a problem that none of them have solved. It is called the hard problem. The philosopher David Chalmers named it that in the 1990s, and the name has stuck because it earns its name. The easy problems of consciousness, and they are not actually easy, only easier, are the problems of explaining how the brain processes information, how it integrates signals, how it produces behavior, how it directs attention. These are difficult scientific questions, but they are the kind of questions that science knows how to approach. You study the mechanism, you map the process, you build the model. The hard problem is different. The hard problem asks why any of that processing is accompanied by experience at all. Why is there something it is like to see the color of a late afternoon sky? Why does the sound of rain carry a quality, a texture, a felt presence? Why is there an inside to any of this? Why does the information processing that happens in a brain give rise to a world that is experienced rather than simply computed in the dark, with no one home to notice? That question has no agreed answer, not even close to one. And it bears directly on the simulation argument in a way that is easy to overlook. Because even if we could build a computational system of enormous complexity, even if we could simulate every neuron, every synapse, every electrochemical gradient in a human brain, we would still not know whether the result would experience anything. We would not know whether there would be a felt quality to its existence, or whether it would simply be a very sophisticated process running in silence with nothing it is like to be it. The simulation hypothesis, in its most ambitious form, imagines not just a computed universe, but a universe full of experiencing minds, minds that feel, that wonder, that lie in the dark and think about their own existence. But whether computation can produce experience is precisely the question that remains open. It is possible that it can. It is possible that experience is a natural consequence of certain kinds of information, integration, and that the substrate truly does not matter. It is possible that the universe is generous in this way, that consciousness arises wherever the conditions are right, in carbon or silicon, or in whatever a simulator might use. It is also possible that experience is more fragile than that, more particular, more dependent on the specific physics of the world we find ourselves in. Current science cannot say which, and so the simulation hypothesis rests, at its foundation, on a question that is itself unanswered. It asks us to consider the possibility of simulated minds while the nature of any mind at all remains, in its deepest aspect, unknown. There is something almost restful in that. Not frustrating, restful. The questions nest inside each other, like rooms inside rooms. And at the center of all of them is the same quiet fact that something is happening here, that there is experience occurring, that the darkness behind your closed eyes is not empty, but inhabited by something that notices, that wonders, that follows a thread of thought down into sleep. Whatever that is, whatever the right account of it turns out to be, it is here. It has always been here. And the universe, computed or not, simulated or original, mathematical or material, contains it. That much is certain, or as certain as anything can be, from the inside of an experience that is still, after all this time, not fully understood. The breath continues, slow and even. The thinking grows softer at the edges, and the question rests the way it always has, patient and unchanged, in the place where knowing ends and something quieter begins. And yet the question does not stop there. It never quite stops at the edge of physics or mathematics or the philosophy of mind. It keeps going, quietly, without urgency, into something that feels more personal. If the universe is computed, if the stars and the distances between them and the slow turning of galaxies are all expressions of some underlying process running on something we cannot see or name, then what becomes of meaning? Not meaning in the abstract, but the particular kind of meaning that belongs to a life, to this life, to the one being lived right now, in this body, in this room, in this darkness. It is worth sitting with that question gently, without forcing an answer. Because the simulation hypothesis, at its deepest level, is not really a question about physics. It is a question about what reality owes us, and what we owe each other inside it. Consider ethics for a moment, just quietly. If the people around you are simulated minds, if their experiences are generated rather than grown from biology, does that change what you owe them? Most philosophers who have thought carefully about this say no. And the reason is simple. If a mind can suffer, the substrate that produces the suffering does not diminish it. Pain experienced in a simulation, if it is genuinely experienced, is still pain. The architecture of the system running it does not reach inside the experience and make it less real to the one having it. This is one of the places where the simulation hypothesis and the philosophy of consciousness meet most directly. Integrated information theory, one of the more mathematically developed frameworks for understanding consciousness, proposes that what matters is not what a system is made of, but how its information is organized, how integrated, how irreducible. A sufficiently complex computational process, under that view, could carry genuine experience, not a copy of experience, not a representation of it, but the thing itself. And if that is true, then a simulated mind is a mind, full stop. The ethics follow from that, quietly, but completely. There is something almost stabilizing in that conclusion. It means that even inside the deepest uncertainty about the nature of reality, the basic obligations between conscious beings remain intact. They do not depend on the answer to the simulation question. They depend only on the fact of experience, and experience, whatever its origin, is present. That much has not changed. The breath continues, slow and even, and the thinking moves on. There is another dimension to this question that tends to surface in the quieter moments of reflection, and it has to do with meaning in a different sense. Not moral meaning, but existential meaning. The sense that things matter, that effort is worthwhile, that the texture of a life has weight. Some people feel, when they first encounter the simulation hypothesis, a kind of vertigo, as if the ground had shifted, as if the realness of things had been called into question in a way that makes them feel less solid. That feeling is understandable, but it may rest on a confusion. The realness of an experience does not come from the substrate producing it. It comes from the experience itself. The warmth of sunlight on skin is real because it is felt. The grief of loss is real because it is carried. The slow satisfaction of understanding something difficult is real because it happens, because it changes something in the one who has it. None of that is altered by the question of what is running underneath. A piece of music does not become less beautiful when you learn that it is, at some level, a pattern of air pressure variations. The beauty is not located in the physics. It is located in the hearing, in the relationship between the pattern and the mind that receives it. The same logic extends further than it might first appear. If our universe is a simulation, it is still the universe we have. It is still the only context in which anything we know has ever happened. The relationships formed inside it, the understanding accumulated inside it, the care extended inside it, none of that is diminished by uncertainty about its ultimate nature. This is perhaps the most quietly important thing the simulation hypothesis offers, not as a threat, but as a kind of clarification. It strips away the assumption that meaning requires a particular kind of metaphysical foundation and reveals that meaning was never located there to begin with. It was always here, in the experience, in the noticing, in the slow accumulation of moments that add up to a life. And the question rests there, not resolved, but somehow less sharp than it seemed at first. There is one more thread worth following before the thinking grows too soft to hold it. The simulation hypothesis, for all its philosophical depth, remains, by the standards of empirical science, a hypothesis without a test. Karl Popper's criterion of falsifiability asks that a claim be capable, in principle, of being shown false. And the simulation hypothesis struggles to meet that standard, not because it is incoherent, but because any evidence we could gather would itself be part of the system whose nature is in question. This is not a flaw unique to the simulation idea. Certain interpretations of quantum mechanics face the same difficulty. Some versions of multiverse theory do as well. They are coherent, internally consistent, and genuinely illuminating. But they sit at the edge of what science, as currently practiced, can reach. Some philosophers argue that this does not make them meaningless, only untestable, and that untestable ideas can still do real philosophical work, can still clarify what we believe and why, can still reveal hidden assumptions in the frameworks we use to understand everything else. The simulation hypothesis does exactly that. It asks, quietly, what we mean when we say something is real. It asks whether the distinction between original and simulated is as clear as it first appears. It asks whether consciousness, if it can arise at all, cares about the medium it arises in. These are not idle questions. They connect to some of the deepest unresolved problems in physics and philosophy. The nature of information, the structure of space-time, the hard problem of experience that has resisted every attempt at a clean solution. And they all converge, eventually, on the same still point, that something is here, that experience is occurring, that the universe, whatever it is made of, and whatever is running it, contains within it the capacity for awareness, for wonder, for the kind of quiet reflection that follows a long thread of thought down into the dark and finds, at the end of it, not an answer, but a kind of peace. The questions do not need to be resolved tonight. They have waited this long. They will wait a little longer. The breath is slow now. The body is heavy in the way that means rest is close. The thinking has grown soft at the edges, the way it does when the mind begins to release its hold on the day. Whatever the universe is, it is the place where this is happening, where the slow rhythm of breathing continues without effort, where the darkness behind closed eyes is not empty, but full of something that cannot quite be named. Computed or not, simulated or original, it is here. And so are you. And that, for now, is enough. The breath continues on its own. No effort required. Just the slow, reliable tide of it. In and out. And somewhere beneath that rhythm, a thought can rest without needing to go anywhere. There is a philosopher named Nick Bostrom who, in 2003, published a paper, not a casual thought experiment, but a formal philosophical argument, structured and precise. It presented what he called a trilemma, 3 possibilities, and the logic insists that at least one of them must be true. Either civilizations like ours almost always destroy themselves before developing the technology to run detailed simulations of minds, or civilizations that do reach that point simply choose not to run such simulations, or we are almost certainly living inside one right now. He did not claim to know which branch is true. He assigned roughly equal weight to each and left the question open, the way a door is left open in a quiet house at night. The argument rests on something subtle, the idea that consciousness does not require biology, that a mind running on silicon, or on whatever substrate a future civilization might use, would be just as real as one running on neurons. If that is true, then simulated minds could outnumber original ones by a ratio so large it has no comfortable name. And a randomly selected conscious mind would, under those conditions, be far more likely to be simulated than not. That thought can simply rest there for a moment. It does not need to be resolved. What is interesting is how the physical world, when examined closely enough, begins to look less like a smooth and continuous thing and more like something counted. The Planck length, roughly 1.6 times 10 to the negative 35 meters, marks the smallest scale that current physics can meaningfully describe. Below it, the concept of distance may lose its meaning entirely. Space itself, at that scale, may not be smooth at all. Some physicists describe it as behaving more like a discrete lattice, a grid of some kind, rather than an unbroken continuum. This is sometimes called discrete spacetime, or digital spacetime, and it is not a fringe idea. It emerges from serious attempts to reconcile quantum mechanics with general relativity. The physicist John Wheeler spent much of his later life thinking about information. He coined a phrase, "it from bit," to express the idea that information is not just a description of reality, but its foundation, that every particle, every field, every interaction derives its existence from binary distinctions, yes or no, 1 or 0, presence or absence. Claude Shannon had given information a precise mathematical form in 1948, defining it as the reduction of uncertainty, treating it not as something abstract, but as a physical quantity, subject to the same laws as energy and matter. And then there is the holographic principle. Jacob Bekenstein noticed something strange about black holes. Their entropy, a measure of the information they contain, is proportional not to their volume, but to the area of their surface. Stephen Hawking confirmed this with careful mathematics, and the implication quietly spread outward from black hole physics into something much larger. If the information content of a region of space is encoded on its boundary, then a three-dimensional reality could, in principle, be fully described by two-dimensional data. The depth would be, in some sense, derived, emergent from a surface. Juan Maldacena made this concrete in a mathematical framework called AD-CFT correspondence, showing that a gravitational theory in a volume is exactly equivalent to a quantum field theory on its boundary. The interior and the surface are not two different things. They are two descriptions of the same thing. The universe, it seems, may carry its own information more efficiently than its apparent dimensions would suggest. Konrad Zuse proposed in 1969 that the universe might be running on a discrete computational substrate. Edward Fredkin developed the idea through the 1980s. Stephen Wolfram argued that simple computational rules could generate all the complexity of physical law. His cellular automaton Rule 110, a trivially simple set of instructions, turns out to be capable of universal computation, of producing, from almost nothing, patterns of unbounded intricacy. The speed of light, in this framing, begins to look less like a feature of space and more like a clock rate, a ceiling on how fast information can propagate through whatever is running things. No signal, no cause, no effect has ever been observed to exceed it. Quantum mechanics adds its own texture to this picture. Energy comes in discrete units. Spin comes in discrete units. Charge comes in discrete units. Max Planck discovered this in 1900, almost by accident, while trying to solve a problem in the mathematics of heat radiation. The universe, it turned out, does not permit infinitely fine gradations. It counts, and the double-slit experiment, that quiet, persistent puzzle, shows that a particle's behavior changes depending on whether it is observed, not in a vague or metaphorical sense, but in a precise, measurable way. Some interpretations of quantum mechanics suggest that reality only becomes definite when information is recorded, that the unobserved exists in a kind of suspended multiplicity. The many-worlds interpretation takes this further, proposing that all outcomes occur, branching endlessly, a vast computational tree of every possible measurement, every possible history. Physicists have also found that quantum error correction codes, the mathematical structures used to protect information in quantum computers, have a geometry that mirrors aspects of spacetime itself. Mark van Ramsdonk and others have proposed that spacetime may be built from quantum entanglement, that the fabric of space is, in some sense, woven from information relationships between regions. And yet, simulating a quantum system is extraordinarily expensive. The computational complexity grows exponentially with the number of particles involved. This is precisely why quantum computers are being built, because classical machines cannot efficiently simulate quantum reality. If our universe is a simulation, the resources required would dwarf anything we can currently conceive. Some researchers argue this makes the hypothesis implausible. Others suggest that a sufficiently advanced civilization might use approximations, rendering only what is observed in detail, leaving the rest in a kind of compressed, unresolved state. The way a landscape in a dream is vivid only where attention falls and vague everywhere else. Silas Bean and colleagues proposed in 2012 that a lattice-based simulation might leave traces in the spectrum of cosmic rays, a faint signature aligned with the axes of a hypothetical computational grid. No such signature has been confirmed. The search continues, quietly, in various forms. The deeper problem is falsifiability. Karl Popper held that a claim must be testable to qualify as scientific. By that measure, the simulation hypothesis sits closer to philosophy than to empirical science. It is not meaningless, but it is, for now, untestable. It shares this status with certain interpretations of quantum mechanics, with some multiverse theories, with questions that may simply lie beyond the reach of experiment. Descartes asked something similar in 1641, whether a powerful deceiver could make all sensory experience systematically false. His answer was the cogito, the observation that the act of doubting itself proves something is thinking. The simulation hypothesis is a technological descendant of that old question, grounded not in theology, but in extrapolation. What it ultimately asks is not only whether reality is computed, but what that would mean. For meaning, for ethics, for the quiet fact of being here at all. Those questions have no clean answers tonight. The body is still. The breath is slow. The mind has grown soft at the edges. Whatever is running this, whatever substrate holds the weight of all these stars and centuries and sleeping minds, it is running now, quietly, without interruption, the darkness behind closed eyes, still and deep.